Institute with the James Webb Space Telescope. I specifically work on the mid-infrared instrument as the detector lead, but I also have quite a bit of my time I spend doing scientific research and specifically research on supernovae. Now, I have the visual of the room here open so I can see when people raise hands. And as I go through, please feel free to raise your hand and ask a question. I'm more than happy to stop and chat about stuff. So first question, and I'm just going to turn my camera off here, is who is familiar with what a supernova is or has heard of it before? A few. Okay, that's good. So just to get started here, I have just a brief synopsis of what we'll do. We'll talk about supernovae and their history. How do they happen? What do they look like when we look at them? Why are they important as a field of study? Then we'll talk a little bit about supernovae and how they relate to JWST. How do we find them with JWST? Why are they important? How are they different? And then some of the specific supernova discoveries that we've got in the last few years. Does anyone have any questions before I get started?
I think we're good.
Okay. All right. So what is a supernova? Like all things, stars, like our sun, have a life cycle. They are born, they live, and they die. They're born from big clouds of gas and dust at the very beginning of the universe and even today. And as these clouds of gas and dust collapse under gravity, they get more and more dense, they get hotter and hotter, and eventually there's so much matter in one spot that you begin to fuse hydrogen into helium. You start nuclear fusion. And this is where stars live most of their lives. It's called the main sequence, and it's where our sun is currently. It's how you get light and energy on the Earth right now. And it'll do this for millions to billions of years. And I just got to pop up on my screen. There we go. And that's, again, that's where our sun is now. But this is dependent on the mass of the star, the size of the star. Small stars will burn hydrogen into helium for billions of years. The smallest stars can last for longer than the lifetime of the universe as we know it. Our sun, for example, will live for about 8 to 10 billion total years. We're about halfway through that. We think the sun is about 4 billion years old. And much heavier, much higher mass stars will live for on the order of 1 billion to several million years. So when stars run out of fuel eventually, one of two things basically can happen. Low mass stars will sort of go through this weird end of life cycle where they puff up and get bigger, and they'll kind of shed off all of their outer layers and turn into what we call a planetary nebula, leaving behind a core that is what we call a white dwarf. High mass stars above a certain amount, usually above 8 times the mass of our sun, will explode in what we call a supernova. And we'll talk a little bit about how that happens. But first, I wanted to show you some images here. These are James Webb Space Telescope images. On the left is the Southern Ring Nebula, which is a planetary nebula. So this was a star that lived on the main sequence. It wasn't very high mass, and eventually it shed all of its outer layers, and there's a white dwarf star at the end, which is kind of driving this bright blue color you see in the middle. Very pretty. And on the right is a supernova remnant called Cassiopeia A. So similar kind of funky looking clouds of gas and dust, and but the differences tell you a lot about what kind of star it was and all sorts of interesting things about the universe. So I included, I hope it will play, this is a short clip that we got from NASA JPL that just sort of explains the different kinds of supernova as like a little pretense to some of the other things I'm going to talk about. So I'm going to try and play that. And if it doesn't work, that's okay. Let me know if you can't hear it. Don't really need the volume though. So this is the first type. This is a type 1A supernova where you have some lowest mass star in a binary companion with a white dwarf, and it sucks the material off of that star onto the white dwarf, and eventually it exceeds some mass threshold, and after that you get a nuclear explosion. A different way that type 1a supernova might happen is if you just have two white dwarf stars that are orbiting each other and they get closer and closer together until eventually they collide and merge, and the same thing happens. You go over this mass threshold and you get a type 1a explosion. Core collapse supernovae are the most common kind of supernovae, where eventually the balance between pressure and gravity is exceeded and the star actually collapses inward on itself and then has this sort of ricochet mechanism which causes it to explode. And then there's all kinds of faster, weirder, funkier looking supernovae where oftentimes the star has, burped out some kind of shell of gas and dust already, and then when it explodes into that shell, it makes it even brighter, it makes it different colors and things like that. So all types of different supernovae, they have different characteristics that can let us know how to differentiate them. So what do supernovae look like when we're actually observing them? Basically, when they explode, as you might expect, they get really bright all of a sudden, over the order of a few days or even hours, depending on the type. And then over time, as that shell of gas and dust expands, it gets dimmer to our eye. And on the right here is what we call a light curve, where you're measuring the brightness as a function of time. And generally, when we're studying supernova, this is one of the main ways that we're doing it. The shape of this light curve tells you a lot about the type of supernova and the elements that might be involved and the mass of the star and all sorts of things. So I want to talk a little bit about why the study of supernova is important before we start getting into the sort of things we're discovering now. The first is dust enrichment. Basically, we live on a planet made of heavy things like iron, nickel, silver and gold, things like that. These are elements that don't exist when the universe began. They had to be produced somehow. Now, in the normal lifespan of a star, you get some heavier elements, things like lithium, carbon, nitrogen, oxygen, all the way up to iron. Iron is the heaviest thing that a star can produce, but after that, the fusion process no longer produces anything heavier. So you have to get these elements somehow, and the way that happens is in supernovae generally. These explosions have a lot higher energy. It's a different mechanic, and you can smash all these particles together and get all kinds of fun stuff. And that is how we think, things like planets and debris disks and asteroids and all that stuff have to have formed. And the content of dust in the universe is important for determining the likelihood that a planet like ours could form and how likely it is that we might find life elsewhere. Another thing supernova are useful for is stellar population studies. And so, like I mentioned, stars have all kinds of personalities. They can be low mass and red, they can be high mass and blue. And those tell us different things about the origin of the universe. And we can measure the populations of stars throughout cosmic history. Then we can learn things about the origin of the universe and how it changed over time. And sort of leading into that, but a little bit different, is the study of cosmology in general. Basically, we can use some types of supernovae, like supernova 1As, to measure distances, and then we can use those distances and the characteristics of the 1As to measure how the fabric of the universe itself has changed. And we'll talk about that a little bit more in a bit. First, so dust enrichment. Generally, when you think of an explosion happening, you think of things being destroyed. And as you might expect, things around supernovae get destroyed. So companion stars get stripped of their envelopes. They can even be torn apart completely. The core of the star itself is often destroyed. And any gas or dust that's in the area also might be destroyed. However, there's obviously still all this stuff around. I mean, we're made of it, so it has to be produced as well. And JWST is giving us insight into that. We can measure supernovae that happened a long time ago. For example, on the left here is a JWST image of supernova 2004 ET. So that was 20 years ago this supernova happened, and we can still see it with JWST. And what we can do is measure the amount of dust that we can see in these stars as a function of time since they exploded. And if supernovae are producing dust and not just destroying it, then we should see the content of the dust increase as a function of time since when the supernova happened. And on the right, you can see that we actually are starting to see that trend. We can see that supernovae do produce dust, and they're seeding the universe with all of this metal and gas enrichment that forms the planet that we live on. So that's super important because if this type of supernova produces dust and we can see these supernova all the way back to the beginning of the universe, that makes it more likely that there's more planets like ours and more people like us. So before I get on to the other topics, I wanted to quickly poll the room about the concept of redshift. So I'm not referring to, the Amazon Web Services application. I'm talking about astronomical redshift. So just a raise of hands, who has heard of this, kind of understands it, knows nothing about it? Okay, a little bit. So it was good that I included this because it's a little bit complicated, but it's very important to what we're talking about in the universe's history. So redshift is basically a measure of time in the universe. Light particles, photons, behave as both particles and as waves. And so when a wave is moving away from you, and this is true of sound as well, it's the kind of thing that happens when like an ambulance drives by you and it makes a weird modulation in the sound. When photons are coming towards you from an object that's moving away from you, the wavelength of the light is shifted, and it's shifted into a redder color. And when we look out into the universe, we can see that the further away we look, the redder things look. And so we can measure distance in terms of this number called redshift. And it has to do with how far away a thing is, how fast it's moving away from us, and the age of the universe at the time that you're looking at it. So it's a little bit complex, and redshift is a logarithmic scale, as you can see along the bottom axis here, but time is along the top axis, also in a logarithmic scale. So you can see at redshift 1 on the right here, it's where we are, where we see all these galaxies that look like how we know them. But as you go further and further back, you get to the very first stars and galaxies after they formed, just a couple million years after the Big Bang. So what does JWST do for us in terms of redshift? Well, as things are shifted redward, they get shifted out of optical passbands. So that's the color of light we see with our eyes. So at some point, we can't see things that are very far away because they're too redshifted. JWST is an infrared telescope that allows us to see things that have been redshifted further away. So at the top here, you have 3 examples of supernovae that have occurred in galaxies for which I've listed the redshift that we've estimated. On the right is a low redshift galaxy at Z of 0.6, only a few 100 million to billions of years old. In the middle is something at Z of about 3, which is difficult to see with HST, but we could see it. And then at Z of about 4 in the JWST region. So from the ground, we can only see to about redshift 1.5, 2-ish. With HST, we can see supernovae out to redshift 2.5-ish, 3. Galaxies higher. But with JWST, we can see supernovae and stars and galaxies all the way back to the very beginning of when stars and galaxies began to exist, which is very important for studies of the universe. So in terms of stellar population, the number of different types of stars tell us about the origins of the universe. If at the beginning of the universe you have lots of big hot stars, that implies that star formation and evolution started happening very quickly right after the universe began. If you have smaller, cooler stars, that implies the universe got off to a little bit of a slower start. Galaxies wouldn't have formed as quickly, black holes wouldn't have formed as quickly, supernova wouldn't have happened as quickly, life wouldn't have happened as quickly. These are the implications we're talking about. And this concept basically is the foundation of what we call the initial mass function, basically how much mass was there in different types of stars. Supernovae can tell us directly about the population of these stars because if we see lots of supernovae, that means that there's lots of really big stars. And that implies a top-heavy initial mass function. If you don't see so many supernovae, it doesn't necessarily mean they're not there. It could just mean you're not detecting them. But if you don't see them, then it means maybe your initial mass function isn't that high. There are other types of supernovae, such as what we call pair instability supernovae, which also imply a top-heavy IMF, because those types of supernovae only occur in the very first stars that were 200 to 300 times the mass of our sun. So if we ever see those, that we know that we are forming those types of stars and that the IMF would have been really high. To date, we've never conclusively detected that type of supernova, but JWST is probably the only one that's able to do it, and believe me, we're looking. So for cosmology, we can use these type 1a supernovae to measure distances because in principle, we think they happen the exact same way every time. They're always the exact same brightness to within some margin, and that allows us to measure a distance. Now, in the late 90s of 1998, two teams led a big program where they used the Hubble Space Telescope to measure the distances to a bunch of supernova 1As at higher and higher redshifts. And what they found was that not only was the universe getting bigger, it was getting bigger at a faster and faster rate. The universe was expanding and accelerating. That's a huge deal because it was not what we thought would happen at all. So this work earned a Nobel Prize, and there's ongoing work today to confirm it and back it up and learn what it implies about the origins of our universe and the future of our universe. There's been a lot of recent work using JWST. So Adam Rees, who won the Nobel Prize for that work, is working on making sure that calibrations of these Cepheid variable stars and supernova 1As are consistent across cosmic time. But then there's this group called the Pantheon Collaboration, which is working on measuring the expansion rate due to supernova 1A to try and determine whether or not dark energy is variable. Now, our current model of cosmology is called lambda cold dark matter, and this is getting very in the weeds, but basically it thinks that the universe is formed of some parts regular matter, the stuff that we're made of and the light that we can see, dark matter, which is some kind of heavy, massive matter that we can't see and we don't know what it is, and dark energy, which is some kind of driving force that we can't see and don't really understand. The implication of some recent measurements by the Pantheon Collaboration imply that the amount of dark energy or what it's doing is maybe variable with time in a way that we didn't expect, is different from the model. But that result relies specifically on whether or not supernova 1A do behave the same throughout cosmic time. Do they always look the same? Are they always the same brightness? And the truth is we don't actually know, because in the near universe, we can't tell the difference between whether dark energy is variable or whether the supernovae are variable themselves. And we'll talk about that in a little bit. But first, let's talk a little bit about how we find supernovae, and specifically with JWST, although it's relatively the same process. We do this with a method called image subtraction, and it's pretty simple. You take one image of the sky, and you wait a little bit, and then you do it again. Pretty simple. You can subtract one from the other, and anything left over will have been something that changed. So when a supernova goes off in an image that you take new with a template that you have before, you can see this little bright dot on the right side here in all of these different filter combinations. You can find dozens of these things, hundreds, depending on the size of the camera you're using. For JWST, we don't technically find that many because the field of view for JWST is very small. It was designed to view small areas very deeply, but not wide areas. There's future space telescopes like the Nancy Grace Roman Space Telescope, which are infrared telescopes with really wide field of views that don't go quite as deep, but they'll find a lot more transients. And it's really expensive to do this stuff with JWST, so what we do is we rely on serendipitous overlap of images. We just scan constantly the archive for new data that happens to overlap old data, and then we subtract them and just see what we can find. And I'll start going through now with some of the things we found. This one, the previous slide, is actually one of our high redshift supernova 1A candidates. It doesn't have a name yet. It doesn't, well, it has a name. It's just called High Z1A for now, but it doesn't have a phone number yet, as we like to say. But this is approximately redshift of 2, so very, very old, very far away. And we're working on a paper for that right now. This is AT 2023 ADSY. The name is not important. We found it in some very deep JWST imaging, and this is at a redshift of 2.9. This is the highest confirmed redshift for a type 1a supernova ever discovered. And it's very faint. It's actually very hard to tell what it was at first. As you can see, this top kind of green and blue image is the actual 2D spectrum we get from the NIRSpec instrument. Very fuzzy and hard to tell what's going on, but with some very careful work from our colleagues, we were able to extract the spectrum you see down below. So that's the amount of light basically as a function of wavelengths, so different colors. And on the left here, you can see the detection image, and I don't know if you guys can see it, but there's these 3 red rectangles on that image. Can you guys see that in the room?
Maybe not so easily.
Not so easily. Well, anyway, the point I was going to make there was just that the rectangles are basically the positions of the slits for our spectrometer, and they don't land perfectly on the source in the middle. So we're missing a little bit of the light from the galaxy and the supernova, which made it even harder to tell what this thing was. But that said, we were able to tell. At least we could get the redshift from it and then use the photometry, the measure of the light curve, to determine what it was. Because in the spectrum, we can see these 2 bright features, which are hydrogen alpha and oxygen 3, which are not supernova 1A features, but they are features of the galaxy that it's in. So we can model those and take them out, but they do tell us what redshift it's at. And yeah, this is the highest ever redshift 1A detected so far by our team. This is another really cool discovery we made. So this is Supernova Hope. It gets a fancy name because it's fancy. What you're looking at here is a massive cluster of foreground galaxies that are closer to us. That's all basically the big white ones that you see. And in the back, you can see these really stretched out galaxies that are distorted by what we call gravitational lensing. The light or the mass of these foreground galaxies is twisting and warping space-time in a way that this one galaxy way behind them at a redshift of 2 is being bent and distorted, and it actually appears 3 separate times. This is the same galaxy appearing 3 times. And a supernova happened in that galaxy. And the light from these images arrives at 3 different times, which is really cool because that means we can measure the supernova as it arrives 3 different times every time we take an image. And we can do the same with spectra. We can get 3 different spectra at different times in the supernova's life in one pointing. So this is great because multiply imaged galaxies can already let us measure what we call the Hubble constant, or how fast the universe is accelerating, directly just based on the time delays. Supernovae in particular help you narrow that down. They help you beat down some of the uncertainty in that measurement. And type 1a supernovae in particular are great because you can get distance measurements directly from them, and they're a little bit better for calibrating that light curve and the time delays. So we were able to get simultaneous spectra and simultaneous imaging of this one supernova at a redshift of 2, which is still really high considering that was like the 3rd or 4th highest ever detected and spectroscopically confirmed at the time. And yeah, so we did a paper on this where we measured the Hubble constant with just photometry, with spectroscopy, and then with those 2 things combined. What you're looking at in this plot, I understand this might be a little bit complicated, but measurements of the Hubble constant, which is basically how fast the universe is accelerating in our local universe, it informs our model of cosmology, and B, it can be done with a bunch of different methods, different types of stars and how they change, It can be done by looking at the cosmic microwave background, and it can be done with supernova. And this is a huge deal in astronomy right now because there's actually this really big tension between different types of measurements. At the bottom, you see what we call early universe measurements, which are the ones that measure the cosmic microwave background, what we call baryon acoustic oscillations. It's all very complicated, but those have a lower value of about 67. There's a big tension with supernova 1A and Cepheids and things like that, which we call late universe measurements. And these things disagree to a level of certainty, something of like 99.9% certain that they're not the same. It's not just measurement uncertainty. So we call this the Hubble tension, and it's a really big deal in astronomy right now. Supernova Hope on its own agrees with the late time measurements. It does not agree with the Planck measurements. So it's just, one extra bit on this pile, and it doesn't really help us get any closer, but it is definitely a key milestone along the path to figuring this out. Supernova. So if you remember, let me see if I can go back to this plot about cosmology. So this plot here on the right, the top panel, is basically the observed magnitude minus the absolute magnitude of the supernova as a function of redshift. And there's a couple lines there that tell you which type of cosmology you're modeling. And one of the lines is the one that we land on, and that's the one that says the universe is accelerating. So one of the projects that we're working on, which I'll talk more specifically about, is trying to extend that plot further in redshift. So all of these black points are the ones that are spectroscopically confirmed, and they're part of the Pantheon sample. This is thousands of supernova 1As, and they all pretty much fall on this line. It's not until you get to higher redshifts that you could potentially deviate from this line in a way that implies that supernovae 1A are brighter than you might expect due to changes in metallicity or luminosity in mass or something like that. But we think they might change. So in this little inset plot here, you can see that these are the highest supernova 1As ever detected, highest redshift ones. The black star is the one I just showed you at ADSY 2023. And the two purple ones are supernova Hope and supernova, what did we call that one? Encore. And then the blue one there is the first one I showed you with the detection image. So we're just starting now with JWST to get out beyond a redshift of 2. Here's another supernova that we detected. This one's a different type of supernova, but this one is the highest redshift supernova of any type detected to date at redshift 3.5, or 3.6 rather. And here you can see those white boxes of the slits onshore much better. The spectra is much stronger. This thing is much brighter than the one we detected before. And the spectrum on the bottom leaves no doubt this is the highest redshift we've spectroscopically confirmed. In the end, this supernova is not particularly interesting. It is a type 2p, probably core collapse supernova at redshift of 3.6, but we do expect those in abundance at that redshift. So all things going according to plan, and as we get more and more templates and more time, we expect to find more of these and at higher and higher redshifts, which is great. And then I'll talk quickly about our ongoing supernova 1A program with JWST, which Josh is a co-investigator on, and we've got money to have some, hopefully, people in Oneonta help us out. So with this program, the idea is a little bit of what we've been talking about, which is we have JWST time, about 75 hours with near spec and near cam. Might actually be a little bit more than that now, which is, I think, the 10th biggest JWST program this cycle. And what we're going to do with that time is we have 10 high Z, what we call triggers. So we don't know when or where supernovae will happen, but we know that they will. And so we plan kind of generic observations to observe them. And then we tell the Space Telescope, hey, one just happened, go look at it now. And we have 5 triggers for redshifts between 2.5 and 3.5, and 5 triggers for anything above redshift 3.5. There's a typo there. And this is what we think is a very good strategy, because here are 2 plots that show some of the purposeful outcomes of this program. The top plot is showing, this one's a little bit complicated to explain, but hopefully the colors will help to guide it. So this is as a function of redshift. So to the right is things that are further away towards the very beginning of the universe. The line in the middle basically says, this is their current model of cosmology, and if everything is correct that we know of, everything should fall on this line. The gray shading is the uncertainty in that model, and the dashed vertical line is basically the minimum redshift cutoff for this program. The red and blue dots correspond to a simulation of detections we might get that would either show or not show that the intrinsic luminosity of a supernova 1A, how bright they are, is either changing or not changing with redshift. If it is changing with redshift, that means that the supernova 1A progenitors, the stars, the white dwarfs that explode, or their companions, are changing with redshift. And what that tells us is that our ability to measure whether dark energy is changing with redshift is dependent on our models of supernovae 1As. So this Pantheon measurement I mentioned earlier wouldn't be as reliable as it claims at the moment. The bottom plot is a little bit simpler. It's basically telling you how many of this type of supernova you expect to see as a function of redshift over some constant area. At the moment, all of the supernova we've detected are in a redshift range where we can't actually differentiate between very big model changes. So as we look back in history, we might see a ton more, or we might see very few. The good news is that if we detect any, even 1 or 2 of them, as you can see with these big bright pink and yellow lines, just 1 or 2 of them would be able to differentiate, or rather put constraints on which model is correct with very little uncertainty. We don't need a huge sample of thousands of supernovae to do that. And finally, I just wanted to talk about our very first trigger with this program. And we're already off to an interesting start, I'll tell you, because when we detect these things, we think we can identify them based just on a few filters of photometry and some of the host galaxies properties of the host galaxies we think they're associated with. So this image on the right, this is a JWST image of some deep field. There's a big bright red galaxy there, and there's a supernova that's circled in green. Now, the program analysts for this data, we found the supernova, we asked them, hey, what redshift is this galaxy at, do you think? So they went and they did some photometric redshift fitting, and they get this beautiful plot on the bottom left here, which says the redshift is 2.6, which is in our range, and it's also what we call a quiescent galaxy. Quiescent means that there's not really any new star formation happening. All of the stars are old. There's a lot of gas and dust, but not very much new young star formation happening, which means there's not very big massive stars that are exploding. So the only types of supernovae we would expect to see in this type of galaxy would be supernova 1As. It turns out that after we triggered the program on this target and followed it up, we got a spectrum and some photometry, and it turns out that this is a core collapse supernova. And the redshift was wrong. The redshift was actually 2, so it was a little bit lower. And had we known that, we maybe could have made some inference. But the fact that the galaxy is quiescent, we probably would have triggered on it anyway, because only 0.3% of core collapse supernova occur in this type of galaxy. It's extremely rare. And so on our first attempt, we found one of the least likely types of supernovae in the universe so far that we know of at a redshift that it hasn't been seen at before. And so all this to say, basically, we're finding new things with JWST all the time. The universe is still a huge mystery, and supernovae are one of the main tools that we're using to help us solve our understanding of the cosmos. And with that, I will take any questions.
All right, thank you very much, Mike. That's great. Any questions from the audience?
Can you hear me, Mike, up there?
I can hear you.
Okay, cool. So if you're doing it via triggering, you basically have to wait for the supernova to explode and then look at it with the telescope. So how do you handle the galaxy subtraction if you don't have a before picture?
Can you just say the last couple words again?
Yeah, how do you handle the galaxy subtraction when you don't have the before picture? You're just taking the photo after the supernova explodes, right?
Oh, I see. Yes. So we actually, what we do is we only get to do these detections when we have a template image. So generally, someone's gone and done some big deep field survey, and then someone will take the telescope back and go look at it again, or there's a parallel field or something that just happens to overlap. And so we're relying a lot on serendipity here, but when we do the subtractions, we're subtracting all of the galaxy out, all of the background light out, and everything that's left is supernova. So we can be fairly confident.
Thank you.
Any other questions? I have a question. So I remember in 2016, we went to San Diego. And at that conference, you asked a question about the crisis in cosmology to a panel of astronomers that included some future Nobel Prize winners, James Peebles, Sean Carroll, Trimble, two others. So what do you think about actually studying the problem now?
Compared to what I thought then, it's a lot of fun. It's an extremely complicated and tumultuous field at the moment. There's so much work going on. It's very competitive, but we're finding really interesting things all the time now, and that's thanks to JWST coming online. People have been waiting for this for years. I think in 2016, I probably would have been sitting in your class and you would have said, James Webb is coming in 2018, and then it didn't come until 2022. So this is all brand new. I'm actually going to Japan next week for a conference in cosmology, and I am giving my talk directly after Adam Rees, who was the Nobel Prize winner for the expansion in cosmology. So he works at Space Telescope. He's based at Johns Hopkins, and he's a co-I on this program as well. So there's a lot of collaboration going on. There's lots of interesting work. I think more than anything, people are kind of desperate to start getting some answers. The conference in 2016, I think the question I asked had something to do with whether or not the math was reliable. If there was some concept in math we weren't aware of. And I think what we're learning is less that it's that and more that the universe is just more mysterious than we know.
I think that's probably fair, yeah. Other questions?
I saw one or two more hands before the first one, so I think there's some more.
Yeah. So the distance of the dust or the distance to the supernova? Oh, okay. So the question is, how do we measure the distance that the dust travels after a supernova?
That is a great question. It depends how close the supernova is. If we have a very nearby supernova, we can measure it in terms of basically parallax or visually how we can measure the angle of separation. So for things in our galaxy or fairly close, we can resolve the dust and see exactly how far apart it moves. For things further away, what we can do is look at the spectrum, and maybe I can scroll back a little bit here and find one of those. So in the spectrum, you get these big emission features, and these features are relatively narrow because they're coming from the galaxy. But for supernova, features tend to be very broad and fat. And what that is telling you is that the element that's emitting that light is moving. And the wider it is, the faster it's moving apart. And so if you imagine it's all coming from a point that was a star, and then you take measurements of it over time and measure the velocity of the dust as it expands in this shell, you can learn how far the dust has moved over time.
Anyone else?
Mike, so type 1, did I understand this correctly? Type 1A supernova, they represent somewhat of a standard candle.
That's right, yeah.
Why?
Why?
It seems like they would be very different from one another.
So the reason that we think that they're a standard candle is because of the mechanism of explosion. If you recall that short video I've included at the beginning of the talk, there's 2, maybe 3 methods we think these things happen, but they all involve a white dwarf. And a white dwarf is what we call an electron degenerate star. It's basically the closest electrons can be together before collapsing and turning into a black hole. And white dwarf stars have a maximum mass. It's called the Chandrasekhar limit. And when they exceed that limit, basically it explodes. And so we know that because when they always explode at the same mass, that they always end up the same brightness. And so if you can imagine, someone holding the same flashlight at various distances, you can see how faint it is relative to where you're standing, and you can measure how far away it is. Now, that's boiling it down a little bit. They do vary a little bit in color and in brightness, and then how long the light curve takes, based on their environment, based on their host star. But we can correct for those things fairly well and get pretty accurate distant measurements from them.
Thank you.
Other questions? I think I have another question. Have you been following at all Wendy Friedman's work on the measuring cosmic distance scale on the tip of the red giant branch?
Not personally. I know it's something our team has kept an eye on, but probably mostly Adam's team has kept an eye on that as they're working with more the stellar things like Cepheids.
Okay. Yeah, and I was just wondering whether you had anything to say about it. But,
not much beyond that. It seems like the work that's going on in sort of validating all of these different ways of measuring distances up the distance ladder, Cepheid stars, tip of the red giant branch, supernovae, they all seem to be self-consistent and sort of confirming that they work, which only makes the Hubble tension worse. So, yeah. One of the keys will be determining whether dark energy is actually varying, and that will give us a little bit more leverage on measuring distances in the cosmology. As far as questions, I'm also happy to take career level questions, grad school level questions, those kinds of advice things too, because I was once sitting where you're sitting, and these talks were very important to me. So I'm happy to answer any kinds of questions at all.
Jack?
Says, what would be like the next direction?
Jack was wondering about what direction might things go after JWST.
After JWST, so there's a few things coming in the future, and specifically as they relate to supernovae. The first is we just had the Euclid Space Telescope come online. That's a European space telescope, very wide aperture. It's in the near infrared, so that's going to be great for helping to discover high redshift supernovae. In just 2 or 3 years now, we're going to have the Nancy Grace Roman Space Telescope, which is another infrared space telescope with a wide field aperture, so it's looking at huge parts of the sky all at once. That will also be kind of out at L2, where JWST is, and cooled. And that is a big deal because it's downloading something like several terabytes of data a day. So again, great for detecting supernovae out to redshift maybe 3, 4. So those are the big things in the near term. On the ground, we also have the Large Synoptic Survey Telescope, I think, which has a new name now, the Vera Rubin Telescope. That's going to do more kind of all-sky survey stuff. Again, terabytes and terabytes of data a night, so big data is a big deal for supernovae right now. And then in the future, the astronomical community just recently kind of got together in a room and decided that we want to build another giant space telescope. And it's going to take 15, 20 years to do, and it's called the Habitable Worlds Space Telescope. You can think of this one as sort of, it looks and acts like JWST, but it's in the same optical passbands as the Hubble Space Telescope. It's sort of a more direct successor to that, much bigger. And that one really has two objectives. The first is big cosmology projects looking at supernovae. And the second one is to detect atmospheres on Earth-like planets specifically, which are really hard to detect right now with anything other than JWST. And even JWST struggles with it. Earth-like planets turns out very hard to see. So those are the two main science missions of that. And you can expect that probably in the early 2040s.
So a little bit of time to wait. But the should last until around then almost.
Sorry, one more time?
JWST should last until about that too.
Yeah, so JWST will last quite a long time. The mission requirement was 5 years, with the goal of 10 years. The European Space Agency did such a good job putting it up there that we think it's going to have 20 to 25 years of life. Yeah. Unless we get more of these solar flares, because we're watching the detectors this weekend.
Gosh. Have there been some issues or?
No, it should be fine. It's just you get all these big cosmic rays and stuff that ruin your data. But yeah.
So, does JWST have any protections in place for that? Sometimes with communication satellites, there are things they do to protect from deep dielectric discharge and things like that. Or do you just see your detectors pick up all sorts of traces?
So there's a lot of shielding on it, especially in the direction of the sun, because the whole idea is to keep it blocked from the sun. But there's low-level cosmic rays everywhere, and they're always going to get through. We also get hit with big, what we think are alpha particles, and those cause what we call snowballs and showers and all kinds of big hits like that. And generally, these aren't an issue. They impact the uncertainty in the data a little bit, but for the most part, we can find them and mark them and get rid of them. But over time, as these things happen, they do impact the performance of the detectors, and this is something we see in space telescopes all the time. Near the end of the mission, the responsivity isn't so great because it's been hammered with galactic cosmic rays for 20 years. So we do expect a little bit of that with time, but we're also fairly good at mitigating it. The bigger issue for Webb has been micrometeoroids. And at the very beginning of the mission, we got hit with this sort of big anomalous one, which at the end of the day didn't have a huge impact, but it was kind of bigger than we thought at a rate that we weren't expecting. And that hasn't happened since, but we have taken measures at this point to specifically try not to point the instrument in certain directions that we think more of those might be coming from to protect the mirrors.
Step?
Scientists numbers. What other kinds of different disciplines can equal contribution to the university?
Well, you might not have heard that, but the question is, besides astronomers, what other types of people make meaningful contributions to the JWST team?
Well, Space Telescope is full of people who aren't astronomers, which is cool. Plenty of people who are electrical engineers, physical engineers, flight operations people who operate the telescope aren't necessarily astronomers. We have a big public outreach department who are, it's their job to take the data and turn it into pretty pictures and come up with outreach programs for the community and share the data with people. And those people aren't necessarily astronomers either. So yeah, lots of people involved who aren't astronomers who play a big role, actually.
Maybe one more question? Seth?
That this definition Pantheon implied that dark energy might be variable. What kind of test would either confirm or deny?
So the question was, you mentioned that the Pantheon sample sort of indicated that dark energy might be variable. And so he was wondering what sorts of tests you might be relying upon to actually make that statement.
Yeah. So this is our plot, but Pantheon has a plot just like this. All of the black points are basically Pantheon points. And they're doing a test sort of just like this, where the red line represents a model of our current understanding of the universe. It's our current cosmological model called lambda CDM. And you can play with the parameters of this model to change the amount of matter, the amount of dark matter, how the universe changes with time. But the red line is what we think is basically the truth right now. In the inset, you can see that there's a little bit of red shading around that line. That's the uncertainty in the model as we see fit at the moment. And basically what Pantheon did was they took all of these different supernovae from their program and different programs, and they made this plot, and they did their best to determine whether the data matched the model. And what they found was that there was a little bit of a shift at higher redshifts that showed that it was a little bit different than our actual best fit for the model, which corresponded with a model that had slightly higher levels of dark energy contribution. So it's a minute measurement. It's actually kind of a complex paper, but our work sort of does the same thing, but at a much higher redshift, and so we're going to have a lot more leverage on that exact test.
Thanks, Mike. So that would actually indicate the early dark energy ID. Is that right?
Yeah, I believe so. Yeah.
Great. Well, I think that's all for time, but we should thank Mike again. And
yeah, thank you for having me. I'm sorry I couldn't be there in person when I was supposed to come a few weeks back. I got sick, but wanted to make sure I got to share all this with you. So.
That's been great. Thanks, Mike. And I'll be in touch shortly too. So
great.
On my flight back from Asia this summer, I saw I met up. Well, I didn't know he was there, but I met a person on the plane who happened to be working on the project for kiosks, I believe it was. So they're actually planning to scan the skies themselves, but maybe not quite the same depth that we might need. But,
yeah, we got to go real deep. Yeah.
So, yeah, but anyway, thank you very much. This was really great.
Yes, thank you for having me, as always.
Take care.
Thanks.
It should record, right? So it's
Maybe in the chat. Oh, like the linking and stuff. Yes, it's the same idea. They do galaxy subtractions before and then they subtract it. And what he was saying about